So we were discussing about the generating pulse waveform, for which we have already discussed the flow chart of that, in which we have concluded that when we want to display the pulse waveform, which will be in the form of 1 and 0, so that will be available only if we put 1010 and 1010 corresponding hexadecimal value into the initialization register. And one thing also has been concluded that for 250 microsecond, 1 should be displayed, and for 250 microsecond, 0 should be displayed, so that one whole cycle of the square wave should persist for 500 microseconds. And we know that the problem it is already given that the system clock period is 325 nanoseconds. So what we are going to do, we are going to make a left shifting of this particular bit, so that this bit will come over here as the D0 bit, and this D0 bit will have to be displayed, and only D0 bit we want to be displayed. So what we want, the rest of the bit should be masked, and for masking we are going to use A and I instruction. So this is how this generating pulse waveform can be done: by initializing the register, copying the AA value into the accumulator, rotating it left, and after rotating it left, whatever is the most significant bit, it will become the least significant bit, and keeping least significant bit as it is and masking all the rest of the bits, and then putting this value onto the port 1 so that it will display either 1 or 0. And we want to have a delay of 250 microseconds, so we will use a delay counter, in which we will be loading certain count value into the register, and then we're going to decrement the count and check whether the count value has been become 0, delay count is 0 or not. If it is so, then we will skip, and we will jump to the next process of copying the value into the accumulator and the rotating left, keeping the most significant bit as the least significant bit, displaying this least significant bit on the output port, and the rest of the bit to be So for this particular purpose, we will be using the program, and the program will be just like this, in which we will be using our instruction move MVID AA, where A will be copied in the D register, and then the D register content will be copied in accumulator, and we are going to make the rotation left side. And after doing the rotation on the left side, we are going to restore the value of accumulator after the rotation into the D register, and then masking all the bits, keeping the D0 bit as it is. And so we will be having, we are going to display it on the port 1, and then counter for the delay is to be counted by loading the count value into the B register, decrementing B, and this process will go on for making the 250 microsecond. And then after that, it is going to jump to the next part, where after the rotation, whatever new bit has been arrived, it will be copied in accumulator. Again, it is rotated left, and so on. So in this way, it is going to be done. So how we will be calculating the value? We have to take the loop process, total T state of the loop, as well as total T state of the output. So as far as the loop is outside is concerned, we have to take care that we have 4, 8, 12, 19, 29, 36, 36, and then last 10. So it is counting around 46. So 46 into 325 is nanosecond is the total time period. So 46 T state multiplied by 325, it will be coming around 14.95 microsecond. And what will be the loop? Loop will be having 4 plus 10, 14. 14 into 325 nanosecond into count minus 1 plus 4 plus 7, 11 into 325 nanosecond. So it is coming around TL will be equal to 4.5, count minus 1 plus this. And so this TO plus TL means outside the loop and the loop value is joined together, and we want 250 microsecond delay. So we are putting here 250 microsecond is equal to 14.95 plus 1, and all the values of the T0 and TL is being added so that we are able to find out the value of count. So count value is coming around 52.4 in the decimal, that is equivalent to 34 hexadecimal. So it means this count value is, if it is 34, then it is going to create a 250 microsecond delay for 1 as well as for 0. So this is how this program is going to work. Next problem related with the counter and the time delay is to calculate the count to obtain 100 microsecond delay and express the value in hexadecimal, assuming 2 megahertz clock frequency. So we have to calculate the value of count to obtain a 200 microsecond delay. So first of all, we have to write a program for that. So we will be putting, since we are making requirement in microseconds, so we will be using single register, 8-bit register to load the count value. So the count will be loaded into the B register, and this MVI B count is going to be loaded in B. And then we will be using simple no operation, which will be consuming 4 T state, and then decrementing the content of B, and then jump on no zero loop. So it will be creating a loop. So the total delay required will be total number of the T state multiplied by time of 1 clock period. Time of 1 clock period is 1 by 2 because it is 2 megahertz, so 0.5 microsecond. So this total delay required is 100 microseconds. So 100 microsecond will be equal to, means total delay required is 100 microseconds. So left hand side will become 100 microsecond, will be equal to 7 plus what? 4 plus 4 plus 4, 4 plus 4 plus 4 plus 10. Plus 10 multiplied by count minus 1 plus 4 plus 4 plus 4 into 7, that is, and total multiplied by 0.5. So this count value, whenever we are going to solve that, this value is equal to 100. So count value will be coming around 1 plus 174 upon 24, that is 8.25, that is 0.8. It means if this count value is 0.8, and if we are executing this particular program, this program will be able to create 100 microsecond delay, because the total number of T state multiplied by the time period of 1 T state will be going to give the total time consumed in this particular program. So with this, we are able to find out that how we can do the 100 microsecond delay. So now we have discussed a lot of things related with the counter and the time delay. Now the next part which we have to discuss is the stack and the subroutine. After the count and delay, we have to discuss the stack and subroutine. You know what is the meaning of a stack. A stack is an arrangement in which the datas are put one over the other at a certain place in the memory, and that memory which will be used as a stack will be pointed by a memory pointer, and that pointer is known as stack pointer. So let us go with the simple explanation of the stack. Stack is a group of memory location in the read-write memory that is used for temporary storage of the binary information during the execution of the program. Now, many times, whenever we are executing a program, we are in requirement of putting data somewhere in the memory so that it cannot be lost. And whenever it is required, we are able to fetch it. And it is also the requirement that whenever data has to be temporarily stored in the memory, we have to keep the data in such a manner that it should be fetched one by one. It should be stored one by one, and it can be fetched one by one. And for that purpose, we will be using the stack. Now, whenever any part of the memory which is used as a stack, the memory location of that particular part of the memory which is used as a stack, the starting memory location will be defined in the main program, And so the space will be reserved for that. Now, since the data is stored in the defined memory location, one over the other, as we stack book, so that is why we call this arrangement as uh, the stack. Now, you can say that a stack can be an arrangement in which the first data which is put can be taken out last, or the last data which can be put can be taken first. So based on this arrangement, based on this philosophy, when we arrange the data in the memory, that arrangement is called stack. Now, the second part of this is the subroutine. Subroutine is a group of the instruction which is used to perform the subtask, and if there is a repetitive occurrences of some instructions in the program, instead of writing repetitively the same kind of set of instruction, what we do, we write that set of instructions somewhere else in the memory, and whenever it is required, we call that set of the instructions which are put in the form of a uh, uh, subprogram. So meaning thereby we divide the program into two parts. One is called the main program and another is called subprogram, where the subprogram contains those set of the instructions which will be repetitively used in the main program. So when we are doing this, it is possible that the length of the program should be more. So that's why, just to avoid this occurrence, what we do, that set of the instruction is put somewhere else in the memory, and that set of instruction in collectively is called the subprogram. So subroutine is a subprogram or which contains certain set of the instructions which will be repetitively used in the main program. So what we used to do, we consider this subroutine as a separate unit which is away from the main program, and the microprocessor is going to transfer the program execution from the main program to the subprogram whenever it is required to execute those part of the instructions. So what we do for that particular purpose, we will be calling from the main program, we will be calling the subprogram or the subroutine. And whenever the subprogram is executed and whenever it is finished, it is getting back into the main program. So the purpose is to write the certain set of the instruction only once at a separate place in the memory. And whenever we are in requirement of executing that set of the program, that set of the instruction by the main program, we call that program so that it will be executed. And later on, when the program which is being called is executed, we transfer the control back to the main program. So that is the third part, that after the completion of the subroutine task, the microprocessor returns to the main program. Now, the subroutine technique is going to eliminate the need to write the subtask repetitively. Thus, it uses memory more efficiently. Otherwise, what will happen if we are writing the same kind of the instruction many times in the main program? It will be executing it many times. So the memory utilization will be reduced while using the subroutine. Now, as far as the stack is concerned or the subroutine is concerned, both are a counterpart of each other, in which the temporary storage is done with the stack. Similarly, temporary storage of the instructions are being done in the subroutine. So anyhow, stack and subroutine will be using separate kind of the memory locations where either the data or the set of the instructions are being stored. So they are going to give a great kind of facility while writing the program. So the application, as far as the application of the subroutine is concerned, that whenever we have to develop a program which is required to solve a bigger problem, so you will be in requirement of the more number of lines you have to write for executing the program, for solving the problem. So why not to divide the program into modules, and each module will be represented by the subroutine. So what we do, these modules are developed independently in the form of a subroutine by the different programmers. And whenever you have to club, all the subroutines are developed, it is clubbed with the main program. Now, this was the introduction about the stack as well as the subroutine. Now let us discuss in detail about the stack. As I have told you earlier also, that stack is a set of memory location which is used to store the information temporarily during the execution of the program. While program is being executed, it may be the requirement to store the result or certain kind of the data separately at a separate place, so that the more memory can be utilized by the main program. So this is also going to create a security also. Otherwise, if you have put some data into the user's area, and that user area might be used by writing a program. So in that case, if certain area you are using to store the data, and you are using the same area for writing the program, so in that case, the program will be overwritten over the data. So it is also safe to store the data. So stack is going to help you in that particular format. So before we are going to use the stack, the beginning of the stack is defined in the program by using an instruction, because whenever we have to use the stack, we have to define in the main program that which memory location we want to use as a stack. So for that purpose, we are in requirement of a pointer, which is the stack pointer. So stack pointer must be loaded by that memory address, where which memory address which we want to use as a stack. So that is why we used to use LXI SP 16-bit memory address. And the purpose of this instruction is to load the 16-bit memory address into the stack pointer. And by doing this, what will happen? The 16-bit memory address will be stored in the stack pointer. And this stack pointer, which contains 16-bit address, will be representing that memory address from where that memory can be used to store the data temporarily in the form of a stack. Once the stack location is defined in the stack pointer, we start storing the data bytes. And whenever we start storing the data bytes in the memory address is one less than the address of the stack pointer, meaning thereby, first of all, we initialize the stack pointer by the top of the stack address. And whenever we want to store something into this stack, first of all, stack pointer is decremented by 1, and then only the data is stored in that memory location. So for example, if a stack pointer is loaded by 3099H, then the storing of the data bytes begin with 3098 and 3097, then 3096 and 30, because it is also necessary to keep the stack top location empty. It should not be filled. It is not filled. So that is why whenever we want to use a certain memory area to be used in the form of a stack, the top of the memory is being used, because whenever we put the top of the memory into the stack pointer, below that memory, we are able to store the data. So that is why the address which is being stored in the stack pointer is known as stack top address. Now, the data bytes of the register pair can be stored on the stack 2 at a time in the reverse order by using an instruction which is called push instruction. And the data bytes are transferred from the stack to the respective register by using the pop instruction. Meaning thereby, while using the stack, we can store a 16-bit data into the memory. Of course, individual memory register will be storing only 8-bit at a time, and we want to store a 16-bit data into the memory, which is working as a stack. So we will be in requirement of 2 memory locations to store that 16-bit data. So the data bytes can be stored from the microprocessor to the stack by using an instruction push. And push instruction is a kind of instruction which will be storing the data from the register pair into the stack. And similarly, the counterpart of push instruction is a pop instruction, whose purpose is to reload the data from the stack back to the register pair. So it means while using the stack, we will be using three instructions very commonly. The first instruction is LXI-SP 16-bit memory address. This 16-bit memory address will be the top of the address which will be stored in the stack pointer. And once we are able to initialize the value of a stack pointer, then only we are able to use the push instruction as well as the pop instruction. Push instruction is used to copy the data from the register pair into the stack, and pop instruction is used to fetch the data from the stack back to the register pair. So let us see how it works. So first of all, we will be discussing about the push instruction. Before using the push instruction, it is necessary that we should initialize the stack pointer. So what we'll be doing, we will be using instruction like LXI SP 16-bit. So what this will be doing, it will be loading the stack pointer by the 16-bit address. Now this loading of the stack pointer register with a 16-bit address. And then we will be using these push instruction. Now push instruction, the format of using the push instruction is push RP, where RP represents the register pair. So push RP means store register pair on the stack. Now register pair will be containing 16-bit data. If I am using HL pair, so H will be having 8-bit number, L will be having 8-bit number, and HL pair will be having 16-bit number. So it is going to store the register pair content into the stack. So register pair can be either in the form of a B register, or in the form of a D register, or in the form of a H. B stands for BC pair, T stands for DE pair, and H stands for HL pair. So whenever we are writing BC pair, push B. So what it will do, it will copy the content of B register and C register into this stack. Whenever we are using push D, it means it will be copying the content of D register and E register into the stack. Whenever we are using H, it means we want to store the content of H register and L register into the stack. And whenever we can also use PSW. Now PSW stands for program status word. Now this is also a register pair. When we combine the two register, one is accumulator and another is flag register. Accumulator plus flag register content, if it is combined together, it is called program status word. So whenever we want to store the content of accumulator along with the flag register status, we will be using push PSW, and it will be storing the content of accumulator as well as the flag register into the stack. So the purpose of push RP is to store the register pair on the stack. This is 1 byte instruction. It copies the content of the specified register pair on the stack. Before it is being started, it is must that a stack pointer must be loaded by the 16-bit stack top address. So what will happen whenever push B instruction, or push D instruction, or push H or push PSW used to execute? What will happen? The stack pointer is first decremented by 1, and content of higher order register is copied in the location shown by the stack pointer. So suppose stack pointer, whatever you have loaded, suppose we have loaded 3099. So whenever 3099 is loaded in the stack pointer and we are executing, suppose push B. So what it will do, it will first decrement the content of stack pointer by 1. Whenever we are going to decrement the stack pointer by 1, it will become 3098. And the content of higher order register, means the content of B register, will be copied in the location shown by SP. Now SP is showing 3098. So 3098 पे B register का data copy हो जाएगा. Again, the stack pointer is again decremented by 1. So it was 3098. Now it will become 3097. So at 3097, the content of the lower order register, means the C register, will be copied in that location, that is 3097. Now BDH representing BC pair, DE pair, and HL pair, and PSW represents the program status word, which contains the accumulator as well as the flag register. So similarly, we can use pop instruction. As we use the push instruction, we can use the pop instruction. Push is used to put the content of register pair into the stack. Similarly, pop is used to retrieve the content from the stack back to the register pair. It is again a single byte instruction, and format of using the pop instruction is pop RP. So pop B can be done, pop D, pop H, and pop PSW. So whenever we are writing pop B, it means whatever is the two stack top location पे दो मेमोरी एड्रेस पे जो भी डेटा है उसको BC पेयर में कॉपी कर देगा. Similarly, D पेयर में, H पेयर में, HL पेयर में या PSW में. So how it works? This is again a 1 byte instruction. How it works? First of all, it is going to copy the content of top of the two memory location of the stack into the specified register. So how it will be done? First, the content of memory location indicated by the stack pointer register is copied into the lower order register. Now you see, whenever we are pushing the data, first of all, the higher order register is pushed, then lower order content is pushed. So whatever is being pushed last has to be taken out first. So that is why whenever we are doing pop operation, first of all, the stack top location, which is represented by the stack pointer, first of all, the content of that memory will be copied into the lower order register. And what will happen? The stack pointer is incremented by 1, and then the content of next memory location is copied into the higher order register, and the stack pointer register is incremented by 1. Now, all these instructions belongs to the data transfer instruction, thus the content of the source are not modified, as well as there is no flag which is going to be affected. Now see the difference between push operation and the pop operation. Since push operation and pop operation are counterpart of each other, push operation is used to store the content of register pair into the memory which is used as a stack. Similarly, pop operation is going to store the content of the memory which is used as a stack into the register pair. But as far as the working is concerned, we have difference in the working. Whenever we are using push instruction, first of all, the stack pointer content is decremented by 1, and then the content of the higher order register is copied, and then stack pointer is again decremented by 1, and the content of the lower order register is copied. That is the property of the push instruction. First of all, stack pointer is decremented, then copying of the higher order register. Again, stack pointer is decremented by 1, and the content of the lower order register will be copied. But in case of pop operation, first of all, whatever is the stack top location represented by the stack pointer, first of all, that content will be copied in the lower order register, and then stack pointer is incremented by 1, and then the stack top location will be copied into the higher order register, and then the stack pointer is incremented by 1. So if you want to closely review the operation of push and pop operation, whenever we do push operation, first of all, stack pointer is decremented and then copying of the higher order register. Again, the stack pointer is decremented by 1, and the lower order register is copied. So it means lower order register content is in the top of the stack, and the higher order is below that. So first of all, we have to fetch the lower order into lower order register and the higher order content into the higher order. So for that, so in case of push operation, so first of all, stack pointer is decremented and then copying process is being done. Again, it is decremented and then copying process is being done. But while doing the pop operation, first of all, copying operation is being done, and then it is incremented by 1. The stack pointer is incremented by 1. Then again, the copying operation is done, and then the stack pointer is incremented by 1. So it means whatever way we are doing push operation, just reverse of that, we are doing the pop operation. That is why push and pop operation are those instructions which are used for doing the stack manipulation while writing a program. So let us go with an example. Suppose I have given an example here in which we have loaded a stack pointer by 3099. Then we have put certain data in the HL pair, that is 4 to F2. Then we are doing push operation, and then at the later on we are doing the pop operation. So what will be happening now? The first instruction will load the stack pointer by 3099, and the second instruction will load 16-bit number in the HL pair register, that is 4 to F2. The third instruction is the push instruction. Now what this will do, it will first SP content 3099 is decremented by 1, so that SP will show now 3098, and at this memory location content of H register, that is 42, will be stored. And next again SP is decremented by 1, so that it becomes 3097, and the content of L register will be stored at that location. So after the execution of first two instructions, a 16-bit number is stored in the stack. And when this instruction push H is over, the content of the stack pointer will be 3097. Now, when 2010 display pop B likha hua hai, when this instruction pop B is executed, this will going to retrieve the content of the content which is stored in the stack back to the register pair B. It means you are copying the content of HL pair into the stack, and then whatever you have stored in the as a content in the stack of HL pair, it will be copying back into the BC pair. So first of all, what it will do now, the content which is shown by the stack pointer is having 3097. So whatever is the content of 3097, first it will be stored in the lower order register. BC pair ka lower order register C register hai. So F2 is first copied in the C register, and then SP will be incremented by 1, so that SP will become 3098. Now again, the content of the stack represented by 3098 will be stored in the B register, and again SP will be incremented by 1, so that it will become 3099. So before the start of this instruction LXI H, the SP was on 3099. But when push instruction is executed, SP will show 3097. When pop B has to be executed, before execution of pop B, SP will show 3097. But after the execution of pop B, SP will show 3099. So in this way, this stack operation used to work. So this is the example. Previously, SP was 3099. HL pair was F2, S42 F2. When push is executed, SP is first decremented so that it will become 3098. And at 3098, 42 means the content of H will be stored. Again, SP is decremented by 1 so that it will become 3097. So at 3097, content of L register will be stored. When pop is executed at that time, SP is having 3097. So 3097 is represented in the SP. So whatever is the content of 3097, that is 42, it is, 3097 is having F2, that will be copied in the lower order register, that is C, and SP is incremented by 1 so that it will become 3098, and the content of 3098, that is 42, will be copied in B. And again, the SP will be incremented by 1 so that SP will become 3099.